Welcome back to lecture 11.1, where we're going to talk about a process which is known by many names. One of them is throttling, but it's also often called the Joule-Thomson or Joule-Kelvin expansion. Now, turns out that Thomson became Lord Kelvin, so those are actually the same person. So those are the same thing. Okay, so we're actually going to start this really with a demonstration, and I'm going to show you a few things that we'll set up a demo, we'll discuss it a little bit, and then we'll actually discuss the result a little bit later. Okay, so let me pause. I'm going to pause a few times throughout this just to get the demo set up, and then we'll come back. Okay, so here's the configuration of the demo. So we're going to have a cylinder of compressed gas. So I have two compressed gases here. Let me show you what they are. The first one, you can see, is high purity nitrogen. See that HP 4.8? That means high purity. That means it's 99.998% pure nitrogen, and it's highly compressed. And the next one we have says 4.5 helium. So that means it's 99.995% helium. Okay, you can see we're nice and safe. We've got our lids, our caps on our compressed gas. Okay, so the next thing we're going to do is we're going to hook up to those compressed gases this configuration. Okay, what you can see here is a standard multimeter, okay, that could read, for example, ohms, but it's not reading ohms right now. I've got this special adapter in here, and it's going to read in degrees Celsius. Okay, so why can it read temperature? Well, it's actually another kind of thermometer, which I actually may have shown you before, which is called a thermocouple. Okay, so this is a thermocouple. I'm going to actually stop and, oh, I don't think I need to stop. Look at that, I can just zoom in. So you can see here that the thermocouple is reading 20.9 degrees C. What is a thermocouple? Well, a thermocouple is actually two special kinds of wires that have been joined together. Let's see if I can zoom in close enough that you can actually see the wires. So there's two wires here that have been joined together into a little ball. And it's actually those two dissimilar metals which actually are going to make what's it called, like a C.B.P effect, I think, where there's a thermal gradient here between, so there's a temperature there, and it causes a voltage, actually a current across there, which this thing can then read. Okay, so a thermocouple, and what I'm going to do is I'm going to actually tape with some aluminum tape this thermocouple to the end of a filter. Okay, so all this filter is, oh, and actually you can watch the thermocouple read my body temperature, flying up to 32, 33. You can see it's a pretty fast, pretty responsive, pretty robust way to read temperature, because it's just two metal wires. Okay, so what I'm going to do now is I'm going to actually take it and I'm going to tape it to this plug. Okay. So what this is it's actually stainless steel, which is little stainless steel balls, which have been sintered together in a furnace until they read So they're all kind of this big porous network, okay? So I'm using this, this nice aluminum tape to get that thermocouple to read the temperature of the plug, or really the gas near the end of the plug, okay? All right, so now that's set up, right? So I've got my thermocouple taped to my plug. I'm going to hook up this to the gas cylinder. Okay, so let's do the helium first. Okay, take off the valve cap. It's a brand new, this one's brand new, so that it's as high as pressure in there as possible. And if we were to read the pressure, it should be about 2,000 psi. 2,000 pounds per square inch. Okay, so that's quite high, as we know. So we did the conversion once in class. We said that a psi is 14.5. So go ahead and take a minute and tell me how many bar or how many atmosphere is 2,000 psi. Okay, getting this guy tightened on here. And now what we're going to do is we're going to have our plug here. And the gas is going to come streaming out of the plug. All right, so we're going to, as soon as I open this cylinder, 2,000 pounds of helium is going to come pouring out this plug. Hopefully we have no leaks. And then we're going to see what happens to the temperature. I'm going to wait a minute for this temperature to equilibrate, and since I've been touching it. And then we're going to actually zoom in and get the reading. Okay? Okay, while we wait for that temperature to equilibrate back to room temperature, before we start the demo, let's go ahead and take a stab at estimating what kind of effect we should see. All right? So we're going to do this expansion. We're going to call it throttling. So let's imagine what we should get. All right. So let's look at this process as we have been as a couple of thermodynamicists. Okay. So this cylinder has a fixed volume, right? So we're not going to worry about the volume, but it does have some pressure and some temperature, right? So P1 and T1. And what's going to happen is we're going to have it come to this plug. And then from the plug, it's going to expand. This gas is going to expand into the room. Okay, so this is our valve, and this is our plug. Okay, so what do we expect to happen? Well, we expect the pressure will change, right? This is high pressure. This is low pressure. And we're going to ask what happens to the temperature. Excuse me. All right, so what happens to the pressure? Well, it goes to atmospheric pressure, PA. All right, so I told you that P1 is around 2,000 psi, which, if you calculate, is about 136 atmospheres. So the pressure in that cylinder of gas is 136 times the pressure in the room. That's quite large. So let's look here at what's going on in this process. Okay, so let's look at that process carefully. Okay, so what I want to do is draw this process like the following. So we're going to have a plug here. We're going to imagine that during this process, we have gas come in at P1 and T1, and it's going to go out at P2 and T2, and And here's my porous plug. But these walls, we're going to make them adiabatic. Right? So what we're going to do is make sure that the porous plug isn't exchanging heat with its surroundings. We're hoping to get the temperature of the gas, right? We don't want to get the temperature of the plug. We want to get a temperature of the gas. Well, we're going to do it here by getting the temperature of the plug, so it's going to be not exactly right, but we'll be close. Okay. So now the first thing is to think about what kind of process is this? How do we understand this process? Well, we know that there's a finite temperature drop. Sorry, finite pressure drop. Whenever we have a finite pressure drop, right, from one end to the other, that we know that this cannot be infinitesimally close to equilibrium. And so we cannot consider this process to be quasi-static. Okay, so we're going to have to look elsewhere. Now, the other thing we know is that we're going to have this process be adiabatic, right? Which means that during the process, we're going to have no heat flow, right? So we're just going to be looking at this thing. So we have no heat flow, and so our Q, our heat in this system, will be 0. We're also going to find out next lecture that really the work in this process has to be 0 as well, because in essence it's a free expansion, but we'll save that part for next time. Okay, so how do we imagine doing this process? Okay, so instead of having our gas flow, let's actually think about the work done if we break this up into a chunk. Okay, so now what I want to do is basically have the same configuration, right? But now let's imagine a piston. Okay, so the piston, so this is P1 and T1. So the piston is going to start one out on this side and the other closed in, so there's no volume there. And then in our process, we're going to go to the following. We're going to push that piston in. So this piston is going to be fully compressed, and that's going to push this piston out, right? And now we're going to have P2, T2. So this is going to have a volume V1, and this is going to have some volume V2. So now when we think about pushing pistons, we can think about this process in terms of our work. It's really impossible to define the work in this process, but now when we imagine this scenario as this process, we can really say what the work is. So let's do when the volume's on the left-hand side, right? So when the volume's on the left-hand side, what's our work? Well, we're going minus PdV, right? So if we imagine, so this was an irreversible process, right? It's also irreversible. Once I've done this expansion, I can't get it back. But here, because I've put these pistons, I can actually imagine a reversible process. I can define a work. Okay? So by putting in this surrogate situation, we can actually solve the problem. Okay, well, so what is our work? We're going to go from, we're going to have minus from V1 to 0 of P1 dV, right? It's going to be a constant pressure over here because as we push this, it's going to go over, right? Just to make it the same as this scenario, constant pressure on this side. So that's going to be simply minus P1 of 0 minus V1, which is P1 V1. So what about on the right-hand side? If you imagine pulling this piston back, or the gas expanding and pushing the piston back. Right? So this, by the way, was positive. So this was work on, right? So the work was positive. So it's on. Let me just check to make sure you can still see that. Just barely, but it looks good. Now let's check the right-hand side. Right? So here we're expecting the work to be negative because the gas is doing the work. It's expansion, right? But we can have that the work is from minus 0 to V2. But we're going to keep it, again, constant pressure. So this is dV. So that's going to be P2 minus P2 V2, right? So because I had the minus sign still, but I will have V2, let's just write it, V2 minus 0. So that's minus P2 V2. So here our work is negative, so this is work by. Okay? Completely as we expect. Okay, so now we have to ask ourselves, how can we figure out what's going on with this problem? Well, when in doubt, invoke the first law and see if it can get you anywhere. Okay, so here we have du is dq plus dw. Now I couldn't have done this for this process, the throttling, but I can really do this process for this because I can define the initial states and final states, right? I have a very specific reversible process, so I can define those works. And so delta U is simply delta W for this scenario because dq is 0. And delta W is going to be, so let's say what this is, U2 minus U1, right, is delta W, which is the work on the left-hand side was P1 V1, and the work on the right-hand side was P2 V2, minus P2 V2, minus P2 V2. Okay, so let's rearrange this. We can see that we get U2 plus P2 V2 is equal to U1 plus P1 V1. Does anybody remember what U equals P, what U plus P V equals what? It was called the enthalpy. This was the enthalpy. So we defined the enthalpy when we were doing our CP, right? So let's So if you need, you can go back and look at that example. But what we were doing was we had our constant pressure by putting a mass on our piston, right? So that applied a constant force, so it applied a constant pressure. And we defined the heat capacity in that scenario. We said this was generally applicable for liquids and gas, but we could come up with a way to do it for gases. And we said that heat capacity was defined as dq dt at constant pressure, or partial q, partial t at constant p. It wasn't partial u, that was CV, right? And we couldn't do that here. But in a process where it was constant pressure, then we could rearrange our first law to be du is dq plus dw. So we can rewrite this as dq is du minus, plus dp dv. Well, so work is minus, just write it, dq minus p dv. So rearranging, we get u plus p dv. Or this is d of u plus d of pv. And because d of pv equals p dv plus v dp. But at constant pressure, this term is 0, right? So we can rewrite it like that, or we can rewrite it as d of u plus pv. So we defined this as the enthalpy, and we said that Cp was equal to partial h, partial t, constant p. Perfect. Let me leave my diagram just in case you want to think about it. Okay, so now we can rewrite this. So we can write this as little cp equals partial h, partial t, constant p, where h is h over n, and cp equals big Cp over n. Just molar quantities. And then we realize we can actually change this. So this is partial h equals Cp partial t. And so we can say little h is Cp t, or big H is n Cp t. Cool. So the key feature is we've now said this process, throttling, which we can model as this piston moving in and out, is constant enthalpy. It's a constant enthalpy process. Throttling, or Joule-Kelvin expansion, Joule-Thomson expansion, is constant enthalpy. So the word for that is isenthalpic. an isenthalp. So it's one more process. But you can see that an isenthalpic process N and CP aren't changing, so it should be also isothermal. Okay, so now we have our expectation, right? When I do this throttling process, I look at the temperature. It should be an isenthalpic process, but it should be also isothermal. Okay, let's stop and take a look at what it actually is. We are ready to see what's going to happen when we do our demo. Just a reminder, we're starting with helium as our compressed gas. Hopefully that thing doesn't go flying from the force when we start this. So, this was a new container of gas. Oh, and look at what's happening. So I think steady state with helium, our number seems to be around 27.5 or 27.2 is what I've been getting. Here's 27. So that's an increase of about 5 degrees. Let's take a look and see what happens with the nitrogen. Okay, I've switched to the nitrogen bottle and it's cooled down to about 22 degrees. Let's open our nitrogen bottle and see what happens. So remember, we went from 22 degrees to 28 degrees. That was a plus 6 degrees Celsius change for the helium. And now we're dropping in temperature with the nitrogen. We've dropped from 22 degrees. We're already at 1.2 degrees Celsius. Let's see how far we go. 1 degree. 0.7. 0.8. So it looks like we're going to bottom out around 0.7, 0.8 degrees. So, 0.5. So this cylinder wasn't brand new, so it wasn't quite as full, so the pressure wasn't quite as high. If I had a little bit higher pressure, we would see a little bit further drop. Okay, so now let's record these and see if we can understand where these temperature drops, where the helium temperature increase and the nitrogen temperature decrease comes from. Okay, so the result of our experiment was that, well, first off, we expected our experiment to be isothermal, but what we got was, for helium, we got a temperature change of about plus 6 degrees C, and for nitrogen, we got a temperature change of about minus 22 degrees, give or take. So now what I want to do is figure out, okay, this one's isothermal. Our expectation is isothermal. That's clearly not what we got. How do we understand this process? So we'll pick that up in lecture 11.2, where we're going to go beyond the ideal gas law.